Welcome to the Big Bang class of 2013. It's great to have you here, Professor Cox. It's great to have all of you students from Ryden here. It's great to have all you folks who are watching online right at the moment. The Big Bang class of 2013 is part of the same program as the Big Bang Fair, which is taking place at Excel in London. It is, in fact, one of the biggest celebrations of science, maths, engineering and technology for all young people in Britain. It takes place at the Excel on the 14th to 17th of March. Tickets are free and you can book them online at thebigbangfair.co.uk. Professor Brian Cox lectures at the University of Manchester. He also is a particle physicist who works at CERN in Geneva, where the Big Hadron Collider is. So, Professor Brian Cox, without further ado, very welcome to Ryden Community College.
Professor Brian Cox!
Thank you. Thank you. And I should say congratulations. I know you entered the competition. I'm delighted to be here. Fantastic music. And I just wandered around your labs, which I also thought were wonderful. I spoke to a lot of you. I should say, how many of you are thinking of being scientists at some level? Quite a lot of you. I mean, there are I want to talk really about, I've got to stand in a particular place, actually, they told me, so that the camera can see me. So I usually wander around. I'm going to stand here. I'm going to talk about astronomy, of course, because that was my first love. It was really the thing that inspired me to become a scientist. I always thought I was going to be an astronomer. But I thought I'd start with a couple of pictures. I've got a series on the BBC at the moment called Wonders of Life, which really was an introduction to me, or a reintroduction into biology. And I was surprised how much as a science biology had moved on since I studied it, actually back in the 1980s sometime, so probably when your parents were studying biology. And I thought I'd show you a couple of photographs of some of the strange animals. The interesting thing for me about biology, from a physicist's perspective, was learning about how those animals came to be the way they are. Because, as you know, you only have to look outside now. We live on a planet that is absolutely covered in different forms of life. There are, of course, human beings, which are the most complex things we know of in the universe. But there's also trees, and there are blades of grass, and there are birds, and then there are things like this. Have you ever seen one of these things before? You've seen. Do you know what it's called? Does anyone know what this thing's called? An eye. That's it. It's a lemur, which is a kind of a primate. So in some sense, it's quite closely related to us and monkeys and gorillas. But this thing is very unusual because of this. I don't know if you can see there that long, spidery fingers. I've got another picture of the eye here. Look at that. It's one of the strangest things. And look at those fingers there. Now, the question is, why? Why does this thing have fingers? Have you seen the film E.T.? And there's a question. So what about over there? Do you know why it's got those fingers? Anyone there? That's right. The answer is that it uses it. It's like a woodpecker. So this animal, it lives in Madagascar. There are no woodpeckers in Madagascar, but there's food in the trunks of trees. So what the eye does is it gets this middle finger out, which is twice as long as its other fingers, and it taps on the tree bark and it listens until it hears a hollow sound. When it hears a hollow sound, it gnaws through the wood with those bizarre teeth, which are actually teeth like a rodent's teeth. They continually grow, which is different to other primates. And when they've burrowed into the bark, they get that long finger out again, stick it in the bark and get the grub. What is the answer to that? How can it be that something is so perfectly tuned to its environment? Well, the answer is evolution. The answer is that over millions of years, and we think actually that the lemurs on Madagascar have been isolated from the other primates that live in Africa for 60 million years or more, some changes, little changes in their DNA caused at some point one of these, or the ancestors of these animals, to get a very slightly longer finger. And that would have given it a slight advantage. It might have meant that it could access a bit of food that other lemurs couldn't have, which means it was more likely to have children, and those children would have had the gene that had the slightly longer finger, and over time, over thousands and tens of thousands and millions of years, you get this animal that's bizarre and perfectly adapted to go and live in the trees of the forests of Madagascar. A strange animal indeed. Here's another example that I thought you might find fascinating. This is the largest land crab in the world. And you see that these things climb trees. Why? Have you ever seen a crab the size of that before? The reason is they live on just a few islands, and one in particular called Christmas Island, which is part of Australia, although it's right up near the coast of Indonesia. It's a tiny little place. And on that place, there are no predators at all. There are no big mammals, there are no cats, there are no dogs or any kind of animals like that. So the crabs have become dominant on the island. And so the biggest crab, which is the biggest predator on the island, has been able to get bigger and bigger and bigger. And indeed, these things are quite intelligent. And actually, when I was filming with one of these things, it went into my bag, which I'd left down, and stole money out of my bag and ran off. So they're called robber crabs or coconut crabs because they do this. And actually, I heard a story of a girl on the island who apparently had one as a pet and put it on a lead and dressed it up in clothing, like a little doll. So a very strange animal indeed. I just want to flip through a few of these. If you watched my program the other night, you will have seen me hold this thing. It's called a catfish. It's evolved in a very different way. It's a predator that lives in dark, silty rivers, actually in the Mississippi in the United States. And its eyes are no use because the river's full of silt. So what it's done is it's evolved its sense of touch and smell. And in fact, the whole of the fish is essentially a giant tongue. And it can tastes with such precision that it can map out where its prey is in the river just by sensing chemicals across its whole body, and that's how it hunts. And finally, for no reason at all, I thought I'd show you that thing, which is actually going to be in the programme this Sunday, I think. It's a 3-month-old lion cub. Beautiful thing. The interesting thing from the Lion Cubs, the reason we filmed the Lion Cub is because although it looks quite different to me, it is extremely similar in many ways. And indeed, its eyes are almost identical to ours. It uses the same chemicals in its eyes. And in fact, as you look across the whole animal kingdom, even to animals as bizarre as an octopus or a catfish or even insects, then at the basic level, their eyes work in the same way as ours. So a beautiful little lion cub. By the time they're 12 months old, they're too big and too dangerous to go near, essentially. So you can only touch them and stroke them when they're about 2 or 3 months, and then they soon get into fully grown lions. So the question for a scientist is really, those things are beautiful. We can look at them, we can classify them, we can understand how they behave. But the question, particularly for physicists and biologists who are interested in the fundamentals of life, is how? How was it? How did it come to be that Earth is populated by so many wonderfully diverse organisms? And from a physicist's perspective, you want to go back all the way to the beginning. So this is a picture of the origin and evolution of the universe as we know it now. Now, we made a spectacularly precise measurement of the age of the universe quite recently, actually. The current number is 13.75 billion years old. So it's got decimal points after it, plus or minus 0.1 billion years, actually. So there's even errors. I know if you're doing your experiments in the science lab, then you're encouraged to see what is the error on this measurement. If I can measure something, it's 3 centimeters long. Is there an error of 1 millimeter or so in that measurement? Well, we've measured the age of the universe with errors to 13.75 billion years. Tremendous achievement. So the picture is that 13.75 billion years ago, the universe began. Why? We don't know. We don't know the answer to questions such as what happened before the Big Bang. I get asked that a lot. The answer is we don't know. It's out there. It's current research. But we do know that the universe was extremely hot and extremely dense and extremely small 13.75 billion years ago. In fact, everything we can see in the universe today, we think at some point was compressed into something smaller than this room, and actually probably smaller than your head, and in fact probably smaller than an atom. And I'm going to show you in a minute how big the universe is at the moment. So it's a tremendous thought. But what we know is the universe expanded and cooled ever since. And as it cooled, complex things began to, well, initially crystallize out. I'm going to tell you about one of those complex things in a minute. But it's a strange thought that we know fairly well at the moment. And this is one of the things that you can learn as you go on in science to GCSE and A-level on to university, is just how precisely we understand how things began to crystallize out. And just from that ball of energy, 13.75 billion years ago, we get today things like DNA and planets and stars and people. How do you go about finding out? One way is to look up at the stars. The other way is to build machines that can explore the universe by recreating the conditions that were present close to the Big Bang. I'll show you one of those in a minute. But I mentioned that I'd just show you how big the universe is, and this is the best way I know of doing it. So this is a picture of a piece of the night sky. So there's the moon. So if it's clear tonight, it might be clear tonight, you go out, you look at a full moon, then it's that big. There's a piece of sky which is that big relative to the full moon, so a tiny piece of sky. It's actually, another way of thinking about it is if you get a 5-pence piece and hold it up at just about arm's length, perhaps a bit further away, then you'd cover a tiny piece of the sky. And a picture has been taken of that tiny bit of sky. So the tiniest 5-pence piece covering up a little piece of sky. It's called the Hubble Deep Field Image. It was taken by the Hubble Space Telescope, which is in orbit around the Earth. And I'm going to zoom in on that piece of sky. So that's actually the constellation of Orion. If you know a bit of astronomy, you go up and see Orion in the winter sky. So we're going to zoom in to the piece of sky. And this is the most detailed picture ever taken of our night sky, of our universe. It was taken from the Hubble telescope in orbit around the Earth. It was taken over thousands and thousands and thousands of seconds. So the Hubble kept going round, kept taking a picture, so you get more and more detail. And this is the picture. It's called the Hubble Deep Field Image. Now, that piece of sky was empty, as far as we could tell from the surface of the Earth. So imagine looking to the blackest, most boring piece of sky you can. That's what it looks like when you take a very detailed picture of it, and you see that it's not empty at all. In fact, every point of light in that picture, other than about 2 or 3, are galaxies. They're not stars. There are about 3 stars in our galaxy in this picture. The rest of them are other galaxies. Now think about what a galaxy is. They're islands of 100,000 million stars or more, billions of stars. In fact, our nearby galaxy, the nearest one called Andromeda, which you can see if you go somewhere dark on a very clear night, you can just about see it with the naked eye, has perhaps got 1 trillion stars in it. Imagine that, 1 trillion suns. So each one of those points, you can see some of them, you can see that they're not blobs, they're little spirals, and these are galaxies. There are over 10,000 of them in this picture. That's that piece of that 5-pence piece bit of sky. 10,000. When you extend that over the entire sky, there are hundreds of millions of galaxies in the observable universe. The most distant ones in this image, by the way, are some of the most distant objects ever seen. So light travels at, 186,000 miles a second, so what's that? 300,000 kilometers per second. 300,000 kilometers per second. It's taken over 13 billion years for some of the lights from these to reach us. Can you imagine that? 13,000 million years traveling at 300,000 kilometers per second. So they're a long way away. So the universe, what I'm trying to tell you, is very big indeed. Billions of galaxies, trillions and trillions of stars. And as I said, what we now understand is that at some point, 13.7 billion years ago, all that was compressed into something much smaller than this room. It's an incredible discovery. So it expanded and cooled and got more complex. How do we know what happened? How do we know how it started and how it was billionths of a second after it began? Well, we can build experiments, just like the experiments I saw in your science lab to do it. This is the one that I work on, which I'm sure many of you, I should ask you, do you know what this is called? Who knows what this is? It's CERN. It's the Large Hadron Collider. This is the biggest scientific experiment ever built. The red circle there, this is drawn on a picture of essentially France. with a bit of Switzerland at the top. The border is somewhere around there. If any of you have ever been lucky enough to go skiing in France, you might have flown into Geneva. You might have landed at that runway. That's an airport, just to get some sense for the size of this experiment. It's written on in red because it's underground, so you can't see it from the air. It's about 100 meters underground, and it's a big tunnel, 27 kilometers in circumference. Its job is to take protons, of which you're made, the building blocks of atomic nuclei, the building blocks of atoms, takes single protons, and it accelerates them to 99.999999% the speed of light. Incredibly fast. They go round there 11,000 times a second when they're going at full speed, and its job is to smash them together. So it takes one lot of protons and sends them that way around very fast, the other set around that way, and smashes them together. In those collisions, you recreate the conditions that were present around a billionth of a second after the universe began, just for an instant. And our job as physicists is to take pictures of those collisions. And it's like getting a time machine. It's very similar to getting a time machine, sending it back to the start of the universe and taking a picture of what it was like. By the way, I don't want to give you too many numbers, but we can make 600 million of those collisions every second. 600 million collisions every second. Bang, 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 bang. So little big bangs. Remarkable achievement. And we've taken pictures of them. We take pictures of them using cameras, as you would, but they're big cameras. This is a picture of the camera that I work on. It's called Atlas. And I just want to show you, can you see that there? That's a person, right, stood next to the camera. And there's another one there. So this thing, it wouldn't fit in this room. You see the numbers, if it means anything at all. It's 44 meters wide, 22 meters in diameter, and it weighs 7,000 tons, but it really is a digital camera. Those little mini Big Bangs happen right in the middle, and this thing takes pictures, millions of pictures a second. This is a picture of, see these big bits here, these big wheels? They're designed to detect a particular kind of particle, called a muon actually. And this is a picture of those wheels when they were being installed. This is the Large Hadron Collider, that machine, which stretches, remember, 27 kilometers out around France and Switzerland. That's me, by the way, with a little white hat on, so you get some sense of the size of this thing. That's a picture of this machine when it was being built. That's you see there's a real person. There's a physicist stood there with his yellow hat on and he's building this thing. Huge thing. In there, those little collisions happen. And this is a picture of one of the most famous collisions that we generated just about a year ago, actually. This is famous because we think this is a creation of a particle called a Higgs particle. Now, Higgs particles are very strange. They're one of the reasons we built the Large Hadron Collider, and we found that they exist. And they're very weird indeed. The idea is that every bit of space in the universe is filled with them. So that doesn't mean space out there, just space out there between the stars. It means this room, right? And in fact, it means the space inside you. So inside you, inside everywhere in the universe, there is a sea of these Higgs particles. And our theory was that we get substance, mass. So you look at our hand, it's a solid thing, it's made of matter. The theory was that it's like that because your little particles, your subatomic particles that make up your body, are bumping into the Higgs particles. And in that process of rattling around inside of all these Higgs particles that are distributed all across the universe, they get mass. And that's the reason, the fundamental reason you're solid. Sounds like a very weird theory indeed. It gets even weirder, actually. If you ask where did they come from, the answer is they condensed out into the universe about a billionth of a second or less after the Big Bang. Like water condenses onto a window. So if you look at a window on a cold winter's day, you see ice forming on the window. In a similar way, we think these Higgs particles condensed out into empty space. You're interacting with them now, which is why you're solid. And that is probably one of the first pictures ever taken of a Higgs particle being created in the Large Hadron Collider. Remarkable thing. One thing I want to say, and I want to emphasize through this little talk, is that the LHC will be there for a decade, 2 decades or more. Its job now, having discovered these weird things, is to investigate them in detail. Now you're, 11, 12, 13, 14 years old. If you fast forward, 6 years, 7 years, 8 years, the LHC will still be running. You can then be a research scientist in just 8 years from now on the Large Hadron Collider. A lot of universities in Britain, my university at Manchester included, but UCL and Imperial in London, Oxford, Cambridge, all those universities send people at the age of, what would it be, 21 or 22, so just 8 or 9 years, to CERN to work on these things. So I hope, one of my hopes, is that at least one of you in this room might be in 10 years' time or 9 years' time investigating the properties of these mysterious particles. We need to know how they behave now. We know they exist. We don't know precisely how they work, why all this stuff condensed out into the universe a billionth of a second after it began. Why? Questions that scientists ask. So, one of you, put your hand up. Who will it be? Who would fancy working at CERN? And there's plenty, yeah. It can be more than one, right? There are plenty of research scientists needed at CERN. Wouldn't that be fascinating? By the way, there are other things CERN is looking for. It's looking for things like extra dimensions in the universe. That sounds strange, doesn't it? This room is three-dimensional. So three-dimensional means you need 3 numbers to specify where something is. So if I wanted to get over there into the corner, I'd have to walk a certain distance that way, a certain distance that way, and a certain distance that way. We think there may be, or it may be possible, that there are other dimensions in the universe. They might be curled up. They might be about 1 millimeter above our heads. But because light doesn't travel through them, we can't see them. Fascinating. They may be discovered at CERN. Lots of interesting questions. So I'm glad that about, 20 of you or something, or 25 said you might fancy working there. It's still going to be there when you're doing your PhDs, if you do degrees in physics or engineering, mathematics. So that's CERN, one of the great discoveries actually in the last 100 years of physics, which was made last year. Let's move on outwards. So I talked about the Big Bang, 13.75 billion years ago. We've talked about what happened in the first billionth of a second, which we're investigating at CERN, these Higgs particles and things. Fast forward on, and about 5 billion years ago, just a bit less, a cloud of dust and gas, which was actually made probably by stars that had lived and died, condensed into our solar system. Now, our solar system is a place that we're exploring now in detail. And again, I'm going to show you a few pictures and give you some ideas of what you might want to work on in solar system exploration in the next 10 years or so. But this is the heart of the solar system, the sun. It's worth reminding ourselves how large and powerful and remarkable the sun is. And this is a real picture. It's not a computer graphic. It's taken by a spacecraft whose job it is to observe the sun. You can fit 1 million Earths into there. So to get some sense of scale, 1 million Earths inside it. Surface is about 6,000 degrees centigrade or Celsius, which is quite cool, actually. The core, 15 million. And the atmosphere, bizarrely, is over 1 million degrees. That's one of the great mysteries. We're beginning to understand why, but think of it, it's rather strange. The surface is 6,000 degrees, the atmosphere is 1 million degrees. So there are great unsolved mysteries, things that we don't know about the way that stars work. What we do know is it's burning hydrogen into helium. So it's assembling the simplest element in the universe into a more complex element, helium, and in the process releasing energy. It's burning 600 million tons of hydrogen every second into helium, fusing it together. To make 596 million tons of helium, it's losing 4 million tons of mass a second as energy, which is why the sun shines, and despite the fact that it's so big, it is so hot and so bright in the sky. So there's the sun. Move outwards, and I wanted to show you this because I think it's a beautiful photograph. This is a photograph, a movie of Earth, but it's an interesting movie of Earth because you see there aurora, the northern lights. So it's a movie from a spacecraft in orbit around the pole, Earth's pole. That would be the South Pole because you can see Australia rolling into view there. This is the wind from the sun interacting with the Earth's magnetic field. The Earth's magnetic field protects us. It's a thing you detect with a compass, protects us from that wind from the sun. But at the poles, it gets the wind from the sun can get in, and it can shake the molecules in the atmosphere of the Earth, the oxygen and nitrogen molecules, and they give off light. And that's the light you see as the Northern Lights. I thought this was a beautiful picture to show of the Earth. So the question is, we understand roughly how the universe evolved from a billionth of a second after it began. We understand how solar systems form. Indeed, we've seen many other solar systems forming. How did life begin? I started the talk by looking at the eye and the catfish, and we talked about us. How did that begin? It's another one of the big questions. The answer is we don't know. But again, this is an area that research is very active in now. So if you're interested in biology, rather than physics or chemistry or astronomy, biology is moving at an increasingly fast rate. And there are really strong, firm theories about how life began. Don't know for sure. One of the theories is that it may have begun about 3.8 billion years ago. We know that quite accurately, actually. So not long after the Earth formed, we see evidence of life appearing on Earth. One of the theories is it began deep below the oceans of Earth in what are called hydrothermal vents. So these are pictures of these vents, very, very deep. You're talking miles, kilometers below the ocean surface. And it's where little undersea volcanoes, essentially, from the heat from the Earth's core, driving up through the ocean floor to make these structures where you get super hot water, minerals, all sorts of things like carbon, all the things you need to make life are cooked almost in these environments. And one of the reasons that we think that life may have began deep below the ocean 3.8 billion years ago is remarkably, in a way, these conditions are recreated in every cell in your bodies. So every cell in your body now, if you look at your finger, or you look at your arm, or you look at your friend sitting next to you, the cells in their bodies are doing some of the chemistry that we think occurred on the Earth 3.8 billion years ago. It's not the chemistry of the Earth today. The Earth was a very strange place 3.8 billion years ago. The oceans were very acidic. There was no oxygen in the atmosphere because there were no plants to put the oxygen into the atmosphere. And yet, in a way, our cells in our bodies are recreating those conditions. What's the answer? Well, the theory goes that that's because life began in those strange conditions all that time ago, and that's the way it's always done it. So it's almost right to say that when life left the vents, it put a bag around this chemistry and took it with it. And in a sense, you are that bag around the chemistry of the early Earth. Fascinating ideas, theories at the moment. But I just met a friend of mine, actually, I should say, at UCL the other day, at UCL in London, one of the universities in central London, who's built a little reactor. They built a little thing which is recreating these conditions as best as we can, as far as we know, to see what happens. Now, he's not expecting anything to crawl out of his test tube, but what he is expecting, possibly, is to see complex molecules, the molecules somewhat like the molecules that make up you and me, emerging from that little reactor. Very cutting-edge research. And over the years, that's going to become more and more interesting. So I suspect that this area of biology, the origin of life, is going to get more and more interesting. More and more people are going to do it. And again, in 10 years' time, we're going to need biologists who are interested in the origins of life to go and explore that. Just before I finish and take some questions, I wanted to step out a little bit more and keep on this theme of life, exploring the solar system in this context to see if we can answer the question, are we alone in the universe? It's kind of related to those vents, because the idea now, one of the modern ideas in biology, is that everywhere, well, it's a theory, everywhere you find conditions like that, you find life. Life is inevitable. If you get water, you get volcanic activity, you get the right mixture of things and the right lengths of time. Is that right? Or is it that life is unique or very rare in the universe and Earth is a unique place? Well, there are other places in the solar system we've already found where conditions may exist that are similar to those vents. This is a picture of Saturn, beautiful photograph. Here's another picture. It looks like a computer graphic. It's not, it's a photograph taken from the Cassini spacecraft, which is in orbit around Saturn now. It's been there for many years taking pictures like this. I was talking to someone in the lab earlier, actually. We were talking about Saturn's rings. You see the rings there, very famous, beautiful structures. This is a picture edge on. The rings are 100,000 kilometers thick. They're made of water ice primarily, but they're only, if you look at the thickness there, it's about 2 or 3 meters. Imagine how delicate that is. 100,000 kilometers in that direction, 2 or 3 meters in that direction. And this is one of the moons of Saturn, which was in the picture, called Titan. Fascinating place. There's Titan again. Again, this is not a computer graphic. That's someone's taken a picture from Saturn, in this case Cassini. There's another little moon up there, actually. You see the intricacy of the rings. The interesting thing about Titan is this. This is a close-up of Titan. This is an atmosphere. It's like Earth's atmosphere. It's blue sky. That's what you see there, the gases in the atmosphere, much thicker than the Earth's atmosphere. Now, Titan's a very cold place, but it's interesting because we've landed on Titan. The European space probe, Huygens, parachuted through this atmosphere a few years ago now, and it landed on mushy, wet ground. Now, it wasn't water because it's very cold on Titan. It was actually methane. So if you have a barbecue in the summer, you might use one of those gas canisters with methane in. At these temperatures, methane can be a liquid. So Titan is a place where there are rivers of methane. There is methane snow falling on the surface. There are oceans of methane. And people are already speculating that possibly there might be some kind of very strange forms of life on Titan. Could it be? There's lots of liquid. There are rivers and there are oceans. And it's a very strange place, but a place that's not covered in water, that's covered in methane, although there may be some evidence that there may be remains of water perhaps below the surface. A very interesting place. But we do find water around Saturn. This is a black and white photograph of a moon called Enceladus, which is quite a small moon. It's not much bigger. It's about as big as Britain, actually. It's quite a small place. But Cassini swept over the surface of Enceladus. That's Saturn, by the way. So Cassini swept over the surface of Enceladus and took pictures. And this is one of the photographs it took. This is a billion kilometers or more away from Earth, this little place. Look at these plumes rising up from the surface. Those are water. Those are jets of water spraying up from the surface of Enceladus, which tells us that there must be at least frozen water and perhaps pockets of liquid below the surface of Enceladus. Could this be a place where we find simple microbes? It might be too small, but it's interesting because there's water there. But this is a place where we are very certain there's a lot of water. This is a place that we're going to explore with a space mission again in the next 10, 15 or 20 years. There are plans to send a very dedicated mission to go and look at this moon. This is the moon of Jupiter called Europa. This is actually a computer animation of Europa and Jupiter, but made from real photographs that were taken by a space probe called Galileo that was in orbit around Jupiter. This moon has got an icy crust. The ice is probably around 100 kilometers thick, but we know that below that ice there's an ocean of liquid water, and there's more water in the oceans of Europa than there is in all of the oceans of the Earth combined. And we think there may be hydrothermal vents below that ocean on Europa. So one of the great challenges, and this is perhaps for 30, 40 years in the future, so when you're in your 50s, perhaps, you're a senior scientist at the European Space Agency or NASA, and you will be designing missions to burrow through that ice. How would you do it? No one's really come up with a good idea. How would you burrow through 100 kilometers of ice to get a submarine into the oceans of Europa to see what's down there? There may be living things in that ocean, we don't know. It's a challenge to you. No one's thought of a way of doing it, but everybody wants to go there because there's an ocean waiting to be explored. And finally, before I take some questions. Nearer to home and nearer to you in time is the exploration of Mars. This is the picture of Mars. This is one of Mars's polar caps. They're ice caps. There's carbon dioxide ice in those caps. There's also water in those ice caps. So we know there's water ice on Mars. At the moment, we're on Mars with a rover called Curiosity. If you go to NASA's website, you can see live pictures, essentially. Every day there are new pictures from Curiosity. It's roving around the surface of Mars to look for signs of water, to understand the geology of Mars, paving the way for the next missions. This is the photograph Curiosity took when it landed. Beautiful photograph. It looks like science fiction again, but that is a photograph from the surface of Mars. Here's another one. Curiosity took a picture of itself. You know, if you've got a mobile phone camera and sometimes you're somewhere interesting, so you take a picture of yourself. Curiosity took a picture of itself with its camera, just like that. I'm on Mars, email it back home. It looks like a computer graphic. That's Curiosity's head, basically, where its cameras are. And it took a self-portrait by taking lots of pictures. If you could try it, probably. You take lots of pictures of yourself and then get a computer and assemble all those pictures together. Curiosity took that picture of itself. It looks like it's in a desert somewhere on Earth, but it's not. That was taken a couple of months ago on the surface of Mars by the Curiosity rover. What I find fascinating about this is that Curiosity is looking for... We're beginning to think now that certainly, almost certain, well, not certainly, but we know there was water on Mars. We know there were oceans and rivers on Mars billions of years ago. Mars has lost its water because it was smaller than the Earth, but we don't know where the water went. It could be that there is liquid water below the surface of Mars. It's one of the things Curiosity is interested in. Where did the water go? How did it vanish? Is it still there in some sense? There's a European mission, part of which is being built in Britain called ExoMars, which is going to go to Mars in this decade or just perhaps towards the next decade, depending on how the funding goes, essentially. But we need people like you. We need British engineers and scientists to work on that mission. Around the time you're 20 years old, that mission will be touching down on the surface of Mars. Its job is to look for life. Perhaps there was life there that's now died out. Perhaps there are still microbes beneath the surface of Mars. And that, I think, is one of the most... If I were you, I would be very interested in exploring the surface of Mars in the next 10 years or more. And finally, could it be that in the next 40 or 50 years we step outside the solar system? Well, this is an animation from the European Space Agency of a journey to our nearest star. Our nearest star, well, it's actually a triple star system called Alpha Centauri. There are 3 suns in orbit around each other, 2 bright sun-like stars, very similar to our sun actually, and 1 small star called a red dwarf, which is called Proxima Centauri. And just a few months ago, we found that there's an Earth-sized planet in orbit around one of those stars. It's called Alpha Centauri b. And so this is an image of what it might be like to journey to that star. It's our nearest star. It's only 4 light years away. It only takes light 4 years to reach us from that star. It is possible. People can conceive already of building spacecraft that could journey to that star. We know there's an Earth-like planet around one of those stars, although it's too hot to support life. It's very close to the star. But we now suspect that there may be a solar system around those planets, because usually if you find one planet, you find more. Could there be a solar system as complex as ours around our nearby star? Quite probably. That's one of the great challenges for the next 10 or 20 years. So that's where I'd like to finish. What I wanted to really show you is that we've answered a lot of questions. We know how old the universe is, pretty much. We know how the universe evolved, pretty much. We know how solar systems formed, pretty much. We have theories about the formation of life, but there are a huge number of fascinating and fundamental questions, many of which should be answered in your lifetime, which means that you are the people to answer those questions. And now I'm happy to answer your questions. Thank you very much. Thank you.
Thank you very much, Professor. We know we've got some questions out there on the floor. I'm sure lots of you've got lots of interesting questions you want to ask Professor Cox. Don't be shy about putting your hand up. Just wait for the microphone to come over to you. Somebody will bring a microphone over to you so that you can ask your question so we can all hear the question. But we'd like to put the first question, we'd like to let the person to have the first question, Professor Cox, is the person who got us to do the original competition, and that's Zach, and he's got a question for you.
Where's Zach?
So Zach's over here.
Zach. Well, thank you for applying to the competition, because it's been wonderful to visit your school. So I want to thank you first for inviting me here.
Okay, so if the universe is constantly expanding, what does it expand into?
It's a great question. It was if the universe is expanding, what does it expand into? The standard answer, as best we know at the moment, is that it doesn't expand into anything because it's space itself, and actually space-time, if you talk up to Einstein, that's expanding. So it's not the right picture to think of a Big Bang in a pre-existing space, like imagine this room is the space and the Big Bang happens in the middle of the room. It's not like that at all. It seems that, as far as we know, space and time began at the Big Bang, and they've been stretching ever since. And so a kind of a related idea, it's very difficult to picture these ideas, but they're fun, right? Is where did the Big Bang happen? Right? You can imagine, you think, well, we're in this big box of the universe. Did it happen over there or over there or over there? It happened everywhere, because all the space that's here now in this room was made, as far as we know, at the Big Bang. So the Big Bang happened everywhere. So it's not expanding into anything. It's very difficult to picture that. What I should say is that the theory that deals with this, the underpinning, it's called Einstein's theory of general relativity. He wrote it down in 1915, and it's still our best theory of space and time, and the theory upon which all these interesting and strange ideas rest. And you learn that. It's quite tricky because it's all about curved space, but you learn it in a physics degree. So if you do a physics degree, you start learning about these ideas. It's just you learn about them because the maths is a bit hard, to be frank, because it's all about curvy space. What's that, Doctor Who, isn't it? Curvy, wiggly, wobbly, spacey, timey. That's what it. That's it, basically. So it's a great question.
Gregor.
Is there a possibility of something exiting the universe? So, like a planet? Yeah.
Outside the universe?
Yeah.
Well, yeah, I mean, interestingly, I just mentioned it very briefly, looking for extra dimensions. So, I suppose it depends how you define the word universe. I mean, you could just say it's everything that exists, and then obviously you can't have anything outside it. But one of the theories is that we imagine that we're not in this three-dimensional space. Imagine that we're just forget one of the dimensions. So imagine we're on a sheet. So imagine we lived on the surface of a sheet of paper, right? And imagine the forces of nature, particularly light, travelled on the sheet. And then there's another force called the nuclear force, the strong nuclear force that sticks your atomic nuclei together. Imagine that only works on the sheet as well. And imagine there's another force called the weak nuclear force. Imagine that only works on the sheet. Then what would happen if there were another sheet, another universe, if you like, just floating a millimetre away, let's say? Well, you wouldn't see it because light is confined to your sheet. You wouldn't feel it because the forces don't come off the sheet there. So it could be there. Now, if that's true, then we can try and do experiments and say, how would we possibly detect it? Not really well known, but there are some signatures of these extra dimensions, as they were, that you can see at the Large Hadron Collider at CERN. It's very speculative stuff. So it could be, I find this remarkable, that there's another universe a millimetre away from your head in a big sheet stretching out infinity in all directions, and you just don't perceive it because the forces that are exerted on us, that hold us together, don't travel from one sheet to the next. They're called... there's all sorts of theories. There are things called string theory, and also these are called branes. So you often see these B-R-A-N-E-S, like brains, like membranes. And so if you ever want to look on the web, you can look for things like M theory, which is membrane theory in a way. Some people say it stands for that, where you see all these theories about different sheets and different universes. So it's fun stuff. It's completely unintelligible, but it's good fun. Might not be unintelligible to you. You'd have to be a really, if you like mathematics and you want to practice a lot and you want to be a theoretical physicist, these are the kinds of things that theoretical physicists are beginning to think about.
We've got some questions, Professor Cox, that's come through from the TES, various links today. One of them is from Cameron Botting. He's in Year 7, and he's at the Henry Beaufort School in Winchester, in Hampshire, and he asks, you work on the ATLAS experiment in CERN. What exactly is this experiment?
Well, ATLAS, I mean, I showed a picture of it in my talk. It's essentially, it's one of the 4 cameras that sit there and take the pictures of the collisions at the Large Hadron Collider. It was built, I should say, there are physicists from, now on ATLAS, there are something like 35 different nationalities working on ATLAS. Some of it was built in the UK. So universities, when you first encounter university, the people here that want to go to university, you'll go there and you'll be taught. But you'll be taught by people in the main that do research. And at Manchester, for example, we have a big research group, myself included, who work on ATLAS. And in the university, there's not only the teaching, the lecture theatres, there are labs where we built parts of that experiment. So we built it there, and we took it to Geneva, we installed it, and we make sure it works. So the universities are an interesting place to be, because you're surrounded by, you can wander around, you can go to the lectures, but you can also go and see your teachers, the lecturers, who are doing their experiments. I mentioned another one with a friend of mine at UCL who's got this ancient Earth in a box, where he's looking to see how life may have begun in the university. So that's one of the great joys, actually, of going there, that you can see where ATLAS was built, or parts of it were built. If you can join in, actually, I mean, sometimes when you get to your 4th year, we want people to come and do a bit of work, so you can get involved. You start, as you go through your university career, you start getting involved in the research.
So the ancient Earth is a model of what we could have how life could have started.
Yeah, it's a wonderful thing. It's a tank about that big, but it's a little hydrothermal vent. Going there, bubbling away, trying to see what happens. That's what you do with science. You want to know how life began. You have a theory, so you try and recreate those conditions and see what happens. It's not unlikely that you'll make life, but you might make complex compounds that are the building blocks of life.
That sounds really exciting.
Yeah,
it's the sort of thing I'd want to get involved in. Do we have some more questions on the floors? Guys, can I just ask you, keep your hand up till the microphone comes to you, if you've got a question to ask. Yep, okay, so we've got a question over here for a young man over here. You tell us your name as we start the question for Professor Cox. Keep your hand up there so we all know it's coming to you.
When did time start?
Yes, when did time start? Well, again, so the standard theory is that space and time began 13.75 billion years ago at the Big Bang. However, the next question is why? Or what happened before the Big Bang? So in that picture, you say, well, there was no time, so you can't ask the question. That's quite unsatisfactory. So there are people, and again, this is the future of theoretical physics in many ways, who say, well, maybe the universe has been around forever. But you've still got to explain why it looks like, in our bit of the universe, it was very hot and very dense, and it's been expanding and cooling ever since. So people start building theories about, well, could it have been, I mentioned I was talking to you about these brains, these sheets that we think of. Maybe 2 of those bumped together and separated, and that looks like a Big Bang if you're living in one of the sheets. It's speculative stuff. But there are huge problems with our picture of the universe and questions like that, brilliant questions that we don't really know the answer to. So it's going to take the next generation and the next generation. It's worth remembering that really there was no such science as cosmology, which is the talking about the origin and evolution of the universe, really before Einstein, which is 1915. So we're only talking about a science that's at most 100 years old. We didn't know about the Big Bang until the 1950s, the 1960s. So really, we're talking probably just about in your parents' lifetime, or certainly your grandparents. If you talk to your grandparents, we didn't know there was a Big Bang when they were at school. But we now know there was a Big Bang. But we don't know. So we're going quite fast. But imagine what in your lifetime where we're going to get to. I mean, in 20, 30 years' time, we've had virtually double the amount of time that we've had so far to work these things out.
So let's take another question over there. We've got a guy who's playing in the band at the back there, Hayden. Do you want to ask your question, Hayden? I think you've been burning with this question for quite some time to ask Professor Cox, so let's hear it.
I'm interested in astronomy and cosmology, so how would you say to get started?
That's a great question, because that's what, when I was your age, that's basically what I was asking. I was interested in astronomy. The way to get into astronomy and cosmology is to do physics at university. And the way to do physics at university is to do physics and maths at A-level and anything else you want. And so, and I should say actually, because I've said it before, I think it's really important, I wasn't very good at maths at school. And I didn't think I was very good at maths. What I found was that maths, for me, and for many of my colleagues actually who work at CERN and astronomy now, is something you need to practice at. And so I think many people find it the most difficult thing that they do at school. It's not in itself. I don't think you have to be, well, I know you don't have to be some kind of great mathematician to be a really successful research scientist, but what you need to do is you need to practice at maths, and I found that's what I had to do. And actually it wasn't until I got to university, I just about managed to scrape through A-level, and then I got to university, and it suddenly I realised that because I was doing a bit more of it, I understood how to do it. So that's my advice. My advice, if you want to do astronomy or cosmology, you do physics and maths, and you just practice at maths, and it will come to you. Even if you might be one of those people who it comes naturally to, which is wonderful. Many people aren't though, but virtually everybody can do it if they do a bit of practice.
So let's take another question. We've got a question from Pablo here at the front, guys. This is the guy here at the front. He's got a question for you.
Is there another substance to create life except for water? And if so, like, are there any other places that you know of which contain other life forces?
That's a really fundamental question in biology, actually, at the moment. So people ask the question, what do you need? What's necessary for life? And what are the things that might just have added on to life on Earth? And so we think you need water. And water's a strange thing. It's a very complicated liquid indeed. And again, there's research now, a lot of research going into how water works. It's simple in some sense. It's H2O, hydrogen and oxygen bonded together. But actually the way that those molecules interact is very complicated. And so we think that water is necessary for life. We think that carbon is necessary because it forms 4 chemical bonds, and so it can make these long chain molecules, which are necessary things, DNA, things like that, incredibly complex molecules. Nitrogen is another thing that we think you need for life. But then there are questions like, do you need iron for life? And we have iron in our blood. Is that necessary? Probably not. It's probably one of the... So it's a very active area of research. What's possibly thought now, as I kind of mentioned, is that in these vents in oceans, and there are oceans on Europa, on Jupiter's moon, as well as here on Earth, you get everything that you might think you need. So you have hot water, you have acids and alkali, you have the rock, which has got minerals, and you have nitrogen and carbon and oxygen, gases like hydrogen sulfide, so maybe you need sulfur. So it looks like the conditions are common in the universe for the origin of life. The question is, we need to find it somewhere else in order to know that it happens somewhere else. And that's why Mars, if you're interested in that, one of the best things you can do the experiments like we're doing at UCL now, or you can go and look on Mars and see if life appeared there as well.
Thank you. So we've got a question come... Oh, sorry, we've got a question come from outside here, another one. This is from Grace, who's also in Year 7 in Parkside Middle School, and she asks, why is there oxygen on Earth but not in space?
So it's a brilliant question. I mean, there is oxygen. Well, there's oxygen on planets, not in the atmospheres, though. So there's carbon dioxide all over the place, for example. But free oxygen molecules in the atmosphere, what is it, 20-some% of our atmosphere is oxygen, O2. That got put there by photosynthesis. So it wasn't there before life. And it's not stable in the atmospheres of planets. So you need to constantly replenish it. So on Earth, photosynthesis does it. So plants take carbon dioxide and they take water, and they rip electrons off the water in the process of photosynthesis, which breaks the water apart. And the oxygen in our atmosphere is coming from water. So it's coming from broken up H2O. That's how it gets into the atmosphere. So you need photosynthesis to do it, which is interesting because what we can do now, we're just about on the edge of having the technology to look. We're detecting planets by watching them pass across the face of distant stars. So imagine from Earth, you see a planet float across the surface of a star. You see the light of the star dim a bit, and that's one of the ways we detect planets in different solar systems out there in the universe. And the light comes through the atmosphere. And we're just about able now to use that light to do what's called spectroscopy on the atmosphere, which allows us to tell what the atmosphere is made of. So we can start measuring the constituents of the atmosphere on planets around other stars. And obviously, the first thing we're doing is looking for oxygen. So in the next few years, we're going to start having data where we can start to do that. Again, it's one of the things that you could work on. You could be one of the people that works on the atmospheres of planets around distant stars. Who'd have thought that? But we can do it. And if you see oxygen there, you think, well, likely there's photosynthesis there. So there are plants on that planet.
I think it's amazing we can actually find out there are other planets now around other stars.
Yes, like the one around Alpha Centauri B, as it happens, which is one of the...
And to be able to measure the constituents of that atmosphere is amazing.
Right on the edge. So we're just about able to do, just beginning to be able to do that. And we'll get better and better over the next few years and decades.
So, do we have some more questions here? We've got a question from young lady over here, Holly. Okay.
What happened when you dropped the yogurt in the Hadron? What was it called?
When did I do that?
I don't know. My old teacher asked me to ask you.
I dropped the yogurt.
I don't know.
I don't remember.
The Hadron Collider, I think she's
the Hadron
about.
Collider. That was, I think that was a joke. I don't think I did. No, because, so you can't drop. The thing is that those tubes are sealed tubes where the protons go around, and they're more empty than space, actually. So you've got to get, it's called a very high vacuum. So you can't pour anything into the tube because it would stop working. Because it's very interesting, actually. You think that these protons, they're like electricity, really. So you've got these, usually if you have electricity, you have a wire, and the electrons go down the wire. Well, these are protons, they're going around. But then there's no wire, they're in a tube. So it's very delicate to funnel them. Can you imagine how you managed to send them around 27 kilometers, perfectly controlled inside these tubes? You've got these big magnets to do it. So it's very high precision. So I don't know. I do have a vague memory of someone saying something about yogurt in the Large Hadron Collider, but it would have been a joke.
I seem to remember hearing sometime that the actual magnets, the electromagnets built in CERN, some of them were designed and built in Britain. Am I right on that score? Yeah, and the detectors as well. I mean, Britain's I think it's the second largest contributor to CERN after Germany. So a lot of it is British, actually. And that's the thing, it's not, you think, it's in France and Switzerland, so it's kind of not part of us. We're the second largest contributor. We own that. It just happens to be that it's in France and Switzerland, but that shouldn't stop you visiting, ever, because you're perfectly welcome to visit. And it should not stop you wanting to work there, because it's a British experiment as much as anything else. It just happens to be somewhere else. And there's some great, in the museum, there's some of those great original bubble chamber detectors, aren't there?
Spectacular.
So it's a fantastic
it's been there
trip
since
to make, isn't it?
1954.
So have we got another question out from the floor there, guys? Shall we go to... There's a...
You're very keen, aren't you?
He's
very keen now. He really wants to answer.
Alex, come on then. Let's see if we can keep your hand up, Alex, so we can see who you are, so we can get the microphone over to you.
How do you get the pictures back from Curiosity on Mars so quickly?
Oh, they go from... I mean, you only get them back at the speed of light. They're sent back by radio transmission. But there's actually there are spacecraft in orbit around Mars. So the rovers now can relay the signals up to the orbiting spacecraft, and the orbiting spacecraft can send them. So one of the first things that NASA and the European Space Agency did was get these big spacecraft into orbit, which take a lot of pictures, but can also relay pictures back. So you don't have to rely on the rover itself. You just need to get it up to these other spacecraft. So there's almost like a communications network around Mars now, and a lot of rovers there. I mean, there's still Opportunity and what's the other one called? I've forgotten what it was called now. But there are two little ones that have been there for a long time. This is still operating. Opportunity. What's the other one called? Yeah, there we are. Anyway, doesn't matter what it's called.
I know we've got a question from a young lady. I haven't seen her hand go up, but she was dying to ask this question. She's asked it several times in the lessons, and I can't answer it. So Lydia, do you want to just put your hand up so we know who you are, Lydia? And if you'd like to ask your question when you've got the microphone there, we know you've been asking it, and I haven't been able to answer these in lessons, so we're hoping you can.
What is dark energy and how is it formed?
There's a great reason you can't answer it, because the answer is don't know. So what it does, if it exists, we know what it does, which is that, so the measurements recently, and again, this is only over the last 10 years or so, tell us the universe is accelerating in its expansion. So the thing is that you wouldn't have expected that. Before the measurements were made, you think the universe begins in a big bang, and everything's flying apart, space is stretching, if you like. And then because of gravity, because of all these things like galaxies in the space, they all attract each other. And so the gravity should be slowing the expansion down, because the only force there is gravity, which is attracting, so it's breaking the expansion. But what turns out to be the case is that it's accelerating, so the rate at which the universe is expanding appears to be getting faster. And that's quite a firm measurement now, and it was a great surprise. So Einstein knew that you could arrange for this. And in Einstein's equations back in 1915, there's a little thing in the equations called the cosmological constant, which you can put in, and essentially that does this. It accelerates the expansion of the universe. But then Einstein took it out, and actually once said it was his greatest mistake. So he thought it was a thing that doesn't really exist. It now turns out it does exist, and we really don't know what it is. And interestingly, though, one of the great questions, this Higgs thing I talked about, at face value, the Higgs field would do that. So you say, brilliant, this is very nice. The trouble is, there's so much energy in the Higgs field that it should blow the universe apart. The number is something like 10 to the power 120 times too much. Now, I don't know if you know that notation. It means 10 with 120 noughts after it. So that's a big mistake. I mean, you cannot make, if you get a calculator and do any sum you can think of, you can't get it that wrong. Your calculator won't do 10 with 120 noughts after it. So there's something horribly wrong with our understanding of the way subatomic particles work and the way that gravity works and the way the universe expands. And nobody has a clue. So again, great thing for someone like you to work on. It needs someone to come along with a very good idea and say, no, this is it, this is why. So we've got these two bizarre pieces of evidence. One is the universe is accelerating its expansion, and the other thing is, as far as we understand quantum theory, it should be accelerating a lot faster. And I mean a lot faster. It should have blown itself apart billions of years ago, but it obviously hasn't.
So it's fortunate in some ways, and there's a lot of work to do there, isn't there?
Oh, it's
Could we take one more question that's come through the TES website? And this comes from Class 5 at All Saints Maple. Are we at the centre of the universe?
No, at least I can answer that. No. The point is there is no centre. It goes back to the question I think you asked, it was one of you over there, about the Big Bang, and we were talking about where did it happen. It happened everywhere. So everything is receding from everything else because it's space that's stretching. So all space was there at the Big Bang, and it's always been here, and it's always been stretching. So there's no centre. It's just it's like saying it's like saying if you look at the surface of the Earth, just the surface, where's the start? Well, it's a surface, so there isn't a start. It's like that with the Big Bang.
I think, Professor Cox, we could go on asking you questions.
We could,
and go on asking you questions, but I'm getting the signal here because it's close to time. So we give Professor Cox a really big round of applause. I know we've really enjoyed it. Fantastic.
Thank you. Thank you. I just want to say it's been a real pleasure. It's wonderful to see so many of you so interested. Probably everyone's interested in science. Number of hands that went up saying you wanted to be scientists. I hope at least what I've done is give you a flavour of the point about science is there are great unanswered questions, some of the fundamental questions, but we kind of beginning to see how we might answer them. So please go and answer them because we need someone to answer them. So that's you. So thank you.
Thank you.
Thank you very much.
Apparently there's been about 1,200 other schools tuning in, so I think that's fantastic. So let's give them all a round of applause.
Yeah.